Okay. Okay. So remember what we're talking about. We're introducing elementary functions on the complex plane, and we started off by defining what e to the iy was for y in R. Right? E to the iy we defined to be cosine of y plus I sine y. And then from there we define e to the z, right, where z is some complex number. We define this to be e to the x times e to the iy. Right? And then from there we started looking at properties of the exponential function. We saw that it mapped the plane onto the plane minus the origin, right? Mapped the complex plane onto the plane minus the origin, and we saw that it was 2 pi I periodic, right? So that when you if it took on a value here and you moved up 2 pi I units, right? Then you get the same value, right? So it's 2 pi I periodic. Its period, and its fundamental domain is what you call it. Fundamental domain were these strips of height 2 pi, right? Okay, and then the last thing we saw was that if you restricted yourself to one of these strips, right, which we made closed on the bottom and open on the top, then the function was actually 1-to-1 there, right? So it was in fact a 1-to-1 map from any strip, any of this half open, half closed strips. It was a 1-to-1 onto map from that strip to the complex plane minus the origin. Okay, and that's basically where we stopped. Okay. So once you have just for a moment, just as a remark, once you have the exponential function, one can define the sine function as e to the iz minus e to the minus iz over 2i, and the cosine function you can define as e to the iz plus e to the minus iz over 2. Okay, and again, I'm going to make the comment that this isn't really how you define it, but later on we'll define things properly and see that these identities actually hold. Okay, so later on we'll use infinite series to define the exponential function, the sine function, and the cosine function. And then once we have them, we'll see that these definitions are not definitions, but in fact identities that follow from the series definitions. Okay, because this is really, if somebody says, "What's the sine?" and you say, "Oh, it's this," right? And that's not really a definition of the sine. Okay, and then see that I'm not going to do it, but you can see that various trig formula, hold. Like sine squared plus cosine squared equals 1. The Pythagorean identity holds. You also have addition formula, blah blah blah. Okay, so just as a comment. Okay. But the main thing we want to talk about today is once we get the exponential function is actually the logarithm function. Okay, so let's get back to the main line of the story here. The logarithm. So the definition here, given any z in c minus the origin, we say w is a logarithm of z, and write w equals log z. e to the w equals z. So it's any number for which e to the w equals z. We call that thing a logarithm. Okay, and we know because the exponential function is onto, right, that there exist logarithms for anybody in here. There's going to be somebody back in the complex plane that the exponential function maps onto. In fact, we know that there are infinitely many guys, right? And if you find one of them, you know all of them because they're all going to lie above each other. You know, they're all differing by 2 pi I. They're all going to be that. If you find one of them, you just add integral multiples of 2 pi I to it, and you get all the others of them. So there's always infinitely many of them. Okay. Okay. So periodicity and ontoness. We see that for each C, there are infinitely many W that are log Z. Okay. Now, if we, also as we said before, right, if we take those half open, half closed strips, right, then for each of those strips, there's going to be right, for every Z here, there's going to be a unique logarithm, right, in that strip, right? There's going to be a unique W that gets mapped to that Z, right? You've got this one-to-one map, and so it makes sense. You can talk about the inverse function. Okay, write it this way. We call the inverse function of the exponential function restricted to a y0, the branch of the log lying in a y0. Okay, right. You have the exponential function, and you restrict it to a y0. Right. So the point is that for any y0, this thing is 1-to-1 and onto. Right. And so you have an inverse function, right? And so it's not a you can have now you've got an old-fashioned function. You can actually define a function, log going from here back to that strip, right? Taking Z to log Z plus I theta, where theta is the argument of Z that lies in a y0. So pictures like this, right? Here's your y0, say. So here's your ay0. The exponential function, right, takes that to c excluding 0, right? And then what we call the branch of the log lying in ay0 is the one that that takes z to the unique point here that gets back to z. Right? As we said, there's going to be infinitely many of them, all differing at heights, differing by 2 pi I. Well, one of them is going to lie in here, right? It's going to, which one is it? What's it going to be? It's going to be old-fashioned natural log. So this is the real natural log. When I use this, so convention, whenever I write this is going to be your old-fashioned real function, real natural log. Okay, so it's going to be this value plus I theta, where theta is the argument of z that lies in that thing. Right, so this will be the inverse function of the exponential function restricted to a naught. We call that thing the branch of the logarithm. Okay, so you can maybe for convenience, every once in a while you don't want to deal with the log, infinite values of a log. You actually want to deal with a specific branch, and you can talk about it's more exact that way. Okay, any questions? No questions. Okay. Pretty common. It's common to call the branch lying in a negative pi, the principal branch. Of the log. And it's often denoted with a capital L. So that's just a convention. You say let's call this one where all the arguments are going to lie between where all the arguments of z are going to lie between negative pi and positive pi. I sense some hesitation. Is it clear that this is a log? Is it clear that this is a log of z? Right? What do you need to be a log of z? You need to be a point so that e to this is z. Is that true? Let's take a look. Right? E to the what's this? This is z plus z times e to the I theta, right? Modulus of z times e to the I theta, where theta is one of the arguments is a particular argument of z, right? So it has the right modulus and it has the right argument. So that's this is an argument of z, and we've chosen it to be. This is a logarithm of z, and we've chosen it to be the one where the argument lies in this thing here. Okay, so that's what it means by choosing the branch. Okay. So we see that. Okay. Another bit of notation. Let capital RC denote the argument of z lying in a negative pi. It's called the principal argument. one of them is going to, one of the arguments is going to lie in this range. Let's call it, we're going to call that the principal argument. So using this notation, the principal log is going to be, of course, natural log z plus I principal argument z. Ask questions. Are there any questions? I feel like people are a little confused. Is there any confusion? Anybody confused with this? It's quite possible that there's actually, that all of you understand everything completely, and I'm just misreading your expressions. I have, as I've said in previous classes, I have no sense of people's feelings, nor can I read facial expressions at all. This has been made very clear to me by my wife. I don't know how many times I've said, "Stop being angry," or "Why are you angry about something?" She says, "I'm not angry. I'm not angry. I'm not angry." This has happened so many times that I've just this past weekend I've sort of resolved I'm never going to trust my instinct about how people feel at all. If I can't, I mean, I live with my wife, right? Right? And and yet I don't know her expression. So, let me know if you're confused. Okay, because to me you look confused, but again, I will never trust my instincts about your feelings. Okay. So the principal log, right, is going to be the logarithm whose argument lies in the negative pi region, interval, right? Right, and all the other logs, right? Right, all the other logs are going to be, this plus some multiple of 2 pi I. Yeah.
So just why not always denote the lower
bound
of the 2 pi?
Yeah. So remember that notation, right? With ay naught, and this is sort of a non-standard notation. So you can forget it right after you take this class, right after you read this book. So it's just the thing that goes from height y naught to so this is, if this were a real thing, and this is really y naught I, and this is y naught I plus 2 pi. Okay. So now let's do something sort of interesting. Let's think in more geometrically about what's going on here. If you take the log, let's look at the principal log. Okay, principal log is going to map onto this thing. Right? Here's the negative pi I, positive pi I. And this is solid, this is dotted. Right? You see, the trouble with misreading people's faces is that when it appears that my wife is angry, then I myself get angry. Right? Stop being so angry. I'm not angry. So let's try.
Maybe you just know she's angry before she knows she's angry.
I'm not gonna try that on her. You really are angry. That would no doubt make her angry.
And then you'd be right.
Yeah, it's just like my parents who always would say, "You have no patience. You have no patience." And I think, "Yes, I do."
That's the worst.
Okay, so let's get back to this. Sorry. So let's think. Suppose we take a point on the negative real axis. Okay. the negative real axis. So its argument, right? Its argument is negative pi. Right? Its argument is negative pi. Its principal argument, excuse me, its principal argument is negative pi. Right? When we so it's going to map to some point on the lower bound of the strip, right? Because you're going to get the natural log of its modulus plus I times its principal argument, right? So you're going to get whatever. This is going to be old-fashioned natural log z and plus I negative pi, right? So this. If we start here, then that's the log. The principal log is going to map that point here. That's going to be the image, right? Everyone okay? Right. That's what we say here, right? The principal log is going to get mapped to this thing. This is going to be the this is going to be some real value plus I times the principal argument. That's going to be negative pi. Okay. Okay. Now suppose I look at a curve that goes in a counterclockwise circle. Okay. What happens to the image over there?
Basically goes vertically.
It goes straight up. It goes straight up, right? Because the modulus doesn't change. What's changing is the argument, right? What's changing is the argument, and you can see what the argument is, right? The principal argument starts out at negative pi, and then goes to 0, and then goes to pi, right? So what's going to happen is it goes like this, right? Okay. So thinking about the log, is it a continuous function? Is it a continuous function on the whole plane, say? Or maybe to make it more, to draw your attention to where I want it, is it a continuous function at this point? No. No, right? Because if you approach this point from the top, the values are up here, right? If you approach this point from the bottom, the outputs are down here, right? It's a discontinuous function, right? What's happening rather is that as you approach this point from the top, you are you're approaching the values of the log plus 2 pi I, right? In other words, you're approaching a new branch of the log, right? You're approaching the values for the next branch. Right? So the log corresponds to a negative pi, right? What happens is that of course you're ending up with this plus I r of z plus 2 pi I, right? You're heading towards the next branch, the one that lies in. You're approaching the log. What do you call it? The branch lying in pi in a sub pi. Right. You're approaching the values of the next branch, right? Okay, so it's a discontinuous function. Can you guys see that? Everyone see that? Okay. So what would make sense to make this whole thing into a continuous function? What you should do is do the following. You should say, I'm going to actually cut the complex plane here. I'm going to cut the complex plane here and glue. I'm going to cut from here to infinity, and I'm going to glue this part here to this part on the next plane, right? Where this one is this function. Okay, right? Because then it's good, right? As I come here, what am I going to get? I'm going to end up at the value here of this one, which is this value. Right? You guys see that? Right. As I approach if I walk around the circle from here, I would like, as I go here, not to end up at this point. I want to end up at this point, right? So I'm going to make a cut here, and I'm going to glue this together. Okay. Okay. But the thing is that if you go around again, you don't end up at the values of this guy. You end up at the values of the next guy. So you need to glue another copy. You need to glue another copy of the complex plane onto it. And similarly, if you're going down, well, you've got to go all the way down. You're going to have this infinite sheeted surface on which you could spiral around infinitely, up and down. Okay. And on that infinite sheeted surface, you would have your logarithm function as a one-valued function on an infinite sheeted surface, as a continuous one-valued function on this infinite surface. Okay, right? So, okay. Yeah.
So by doing that, you made the function continuous, but then you gave up the fact that it maps one thing to one thing.
Yeah, that's right. But it was already infinite value to begin with anyway.
Well, not like the restricted version was not.
The restricted version wasn't, but that was only, there was something unsatisfying about only looking at one portion of your entire function anyway. Right. So anyway, this is one way people think about infinite valued functions, okay. Or multiple valued functions. So
okay, how is it not one-to-one?
How is
With this new addition?
it's not. It's now many. It's now. I'm sorry. It is one-to-one. Yeah. It is one-to-one from the infinite thing to
it's
the.
not many values.
Sorry, I've got it backwards. So you can either think of right. You can either think of the log as a for each value, for each number that you choose in the plane minus the origin, there's going to be infinitely many logs of that. Right? It is infinite, right? Remember, right? So you either think of it like that, or right, or you think of it as a one to each point on this infinite sheeted thing. It assigns one value. So it's single valued on this infinite thing, or it's many valued on this one plane. Okay. Right. It's many. I'll say it again. It's infinite valued on the one plane. That's how we started off with it. Or you can think of it as being one valued on this infinite sheet thing. Okay. I don't know. Does it make sense or not? Yes, I am.
Oh, yeah.
Okay. Again, please be really explicit. Yeah. Yeah. In previous classes, as a joke, I said, yeah. So please, make your expressions explicit, like say yes, But now I think it's not a joke anymore. Okay. So there's the comment. It's maybe more natural to think of the log as a single value function on infinite sheeted Riemann surface, this thing that we were just mentioning, obtained by gluing together copies of C minus the origin along simple branch cuts. And I should probably say that, you know, the cut depended on our first choice on the fact that we're choosing the principal log, right? The cut, the reason why we're using negative pi and positive pi as the thing to cut along is because you know, because that's the line of discontinuity for the principal log. If we had started off with some other branch of the log, the cut would have been along some other angle. So there's nothing particularly special about this cut here. It would have been along some other angle every time. Okay. So this proposition, not really going to prove it, but for Z1, Z2 in a punctured plane, one has log of Z1, Z2 equals log of Z1 plus log of Z2. This is not exactly true, but I'll explain in what sense it is true in a second. Argument of Z1, Z2 equals argument of Z1 plus argument of Z2. So, in the sense that both sides represent the same infinite set of numbers. So as an infinite set, as sets, these things are going to be equal. Or equivalently, any chosen values will result in equality modulo 2 pi I in the first case and 2 pi in the second case. Let me do a quick example, show you what I mean. If we look at the log of e times 1, to see that, you know, if I write something like the log of e times 1 is the log of e plus the log of 1, you know, that's true. This is true in the sense that log e is natural log e plus I times the principal argument plus 2 pi z, right? 2 pi n for n and z. Right? That's to say 1 plus 2 pi ni. And log 1 is going to be 0. Log natural log 1, which is 0. 0 plus 2 pi ni. And you see that if I take, this set and add it to this set, again I get this set back. Right? This log e on the left, right? It's this thing. On the right I've got log e plus log 1, and those are the same sets. So in this sense, the logarithm still has its own the property that you would like. Okay. Once you have the logarithm, you can define exponentiation. So complex powers. So recall back in calculus, how does one define a to b, where a is some real number and b is so a and b are real, so a and b are real, but a is b is, say, not rational. Right? How do you define the power of something, when the power is irrational? Right? I don't know if you remember, but one defines, right? Because for rational powers it's easy, right? If I say 3 to the 3 to 3 to the 3.1, right? Well, that's just 3 to the 31 tenths, right? So you can take 3 to the 31, the 10th root of that, right? That's what it means to have a rational power. But what if I have an irrational power here? How do you define it? Right? You can't talk about, maybe you can take limits. Limits is one way, but what one does is this. You define this as e to the b. What one does is use the logarithm function to define irrational powers.
Isn't the logarithm just defined in terms of? Oh, but a is real.
A is real. Okay, so it's sort of a funny thing, right? What you do is you define the logarithm using the integral, right? You define the natural log using the integral, and then you define the exponential function as the inverse of the log, and then from there you can define irrational powers. So we do exactly the same thing for complex numbers. So for complex numbers, let Z and A be complex numbers and Z be non-zero. We define Z to the A as E to the A log Z. Okay. But this is now the new log, right? The complex log. So what is this? Let's expand this. Right? Remember, log Z is the old natural log Z plus I times the principal argument plus 2n pi, right? There's plus multiples of like this thing is plus I R T. Right. natural log z plus I arc z. Remember, arc z is going to be the principal argument plus multiples of 2 pi. Okay. So that's the log is this multiple valued function. Right? It has multiple values. And so what is this, right? This ZA, what we mean by this is e to the a times that term up there. Right? In particular, for example, if we say 1 to the I, okay, let's do it, 1 to the I, what's that going to be? That's e to the I log 1. That's to say e to the I natural log of 1 plus I times the argument of 1, which is 0, plus 2 pi n. Right. So what you get is e to the negative 2 pi n. Okay. Okay. Another example. If we look at z to the 1/2, right? Z to the 1/2. Well, that's going to be e to the 1/2 log z. Right? That's to say e to the 1/2 natural log of z plus I arc z plus 2 pi n. And z. That's to say, I'm going to break this up. So this is going to be z to the 1/2 e to the I arc z plus 2 pi n over 2. And so, remembering that this is going to be, so notice what you get here, e to the I arc z over 2, e to the pi n I. Okay. And if I split this thing up here, you get e to the pi n I. But pi n I is going to be plus or minus 1. E to the pi n I is plus or minus 1. Okay. Just take multiples of, right? So it's going to be plus or minus 1. And so what is this? This is going to be plus or minus z to the 1/2 e to the I arc z over 2. So it's this again. This is the square root function is a 2 value square root function is a two-valued function, as you have known since childhood. Now you're going to know a little bit more about it. So again, one can so let me say like this. I'll say that later. To fix a branch of the square root function, one specifies the branch of the logarithm. Okay, so for example, again, let's choose the principal branch. Let's choose the principal branch, and that will specify one of these branches. So it's either going to be, okay. So then what do you get? Z to the 1/2 is going to be, coming back here, we're going to get Z to the 1/2 e to the I RZ 15. Right? Because what you're going to do is you're going to specify the branch of a log. We're going to choose the principal branch. That means we're going to throw out this. Right? We're going to throw out this, and so we end up with just that. Okay. So this would be specifying one branch of the square root function. For example, to take the square root of 1, that would be e to the I times the argument of 1. The argument of 1, the principal argument of 1 is 0 over 2. Right? And you get 1 to the 1/2, which is 1. Okay. Okay. What this tells you is that in the principal branch, if you specify the principal branch and constrain that branch of the square root function to the positive real numbers, you get the positive square root function that you dealt with before, right, in childhood. Okay, that's the positive square root function. Now, again, let's play the same game. If you let the argument increase, letting the argument increase. So so just now we started from 1, right? Let's let the argument increase and come back to 1 from the bottom. Okay. What that corresponds to is moving up to the next branch of the logarithm, right? So adding on 2 pi here, right? So at that point, in this picture, let the argument increase and come back to 1. Well, when you come back, then what square root do you get? Well, that's going to be 1 to the 1/2 e to the I 0 plus 2 pi over 2. Right? That's to say 1 to the 1/2 times -1. You get -1. So starting here, right, if you circle around, you come back to the other branch of the square root function, and that branch is the one that has the negative square roots of positive real numbers. Okay, and what would happen if you went around again? Well, then this would be 4 pi. And you come back to the positive guys again, and so on and so forth, right? And if you circle backwards, of course, you go to the other one just as well as swing forwards. Okay. So in this case, the Riemann surface that you're talking about is one where when you cross this line in either direction, you're going to end up on another copy, right? So there are two copies. Right? You just cut here. Two copies of the complex plane, and when you cross here, you come over here, and when you cross back this way, you end up coming back over here. Okay, right? It's a two-sheeted surface, right? And you've got a one variable, and you've got a single-valued complex function on this two-sheeted surface, okay, or a two-valued function on a single surface, however you want to think about it. Right? And so you see that the square root function is just one function, right? Although you thought of it maybe as something confusing in childhood, like, well, there's maybe two square root functions, but it's actually just one function united in this way, and you can travel from one to the next. Okay, it's just one function. So now you actually know what the square root function is. Those of you who had me in classes before may have heard me say that that this is the beginning of Alice in Wonderland. This is the model for Alice in Wonderland, right? Lewis Carroll was a mathematician. He thought this would be a great thing for a story, right? Where you pass through some sort of line, the looking glass, and you end up this world where everything is backwards, right? It's negatives of everything, right? Nothing makes sense over here, but you can pass backwards through the mirror to your normal world. Okay, so this is it. This is Alice through the looking glass, right? Or it's descendant the matrix, right? Neo starts off in the fake world, right? In the backwards world, and then how does he get to the real world? He touches the mirror, right? And the mirror creeps over him, and he ends up in the real world, right? I'm glad that you all still recognize the matrix. In some years, it's not going to change.
That's weird, isn't it?
Yeah. Okay. So maybe that's all I'm going to say about this sort of thing. Let's go on to section 1.5, analytic functions. So we're going to start off with a definition that is sort of deceptively familiar. Let F be some, so E is an open set. F be some function on an open set, and let Z naught be an E. If the limit f of z minus f of z naught over z minus z naught as z goes to z naught exists, then we call that limit f prime z naught and say f is complex differentiable to distinguish it from our old definition of differentiable. You could call it complex differentiable, but in general in this class we'll just call it differentiable. This is the course in complex analysis. Okay. So some remarks. One, as usual, equivalently, you can look at the limit of f of z naught plus h plus f of, minus f of z naught over h as h goes to 0. maybe I should use something other than h. I'm going to use zeta to make it clear that this is a complex number going to 0. Okay. Another remark, I think I mentioned this before, holomorphic, analytic, regular, complex differentiable are all basically the same terms. So if you see a holomorphic function, it simply means that your function is differentiable. Analytic function, regular function, it's all the same. Okay. But one warning, in this book, if they say analytic at a point, they actually mean analytic on a neighborhood at that point. So just a warning. Analytic on the neighborhood.
Is that just the book, or is that standard?
Let me think about that. I don't think. I'm tempted to say it's just the book, but I think that's wrong actually. So let me get back to you. I think there's actually a good reason for them to do this, for them to say that. Okay. Okay. So, for example, if we look at f of z equals modulus of z squared. Okay. Turns out that this is differentiable only at z equals 0. So let's look at the limit. Right? So f of z plus zeta minus f of z over zeta, and zeta goes to 0. Right? That's just writing out what this means. This is modulus z squared, so that's z plus zeta times z bar plus zeta bar minus z bar over zeta. Okay. And that works out to be the limit as zeta goes to 0 of z bar plus zeta bar plus z times zeta bar over zeta. Just by arithmetic. Okay. You notice that if we let zeta approach 0 along the x-axis, or along the real axis, if we let zeta approach 0 along the real axis, well then this limit is going to be you get zeta bar plus zeta, right? Because zeta is going to be real. Zeta bar is the same thing as zeta. If zeta is real, zeta bar and zeta are the same thing. So this is 1, right? This is 1, and this is going to go to 0. So you get zeta bar plus zeta. But if you do it along the imaginary axis, what do you get? Well, in that case, this becomes negative 1. Right? Because if you have an imaginary number, right, I, h, let's say that zeta equals I, h, then zeta bar is negative I, h. Right? And you're going to end up with the negative over itself. In other words, negative 1. Right? So you get zeta bar minus zeta. For this limit to exist, those two things have to be equal, right? For the limit to exist, we need it's got to be the same thing no matter along what line you approach it. So you need zeta and z to be equal to negative z, right? But that tells you that z must be 0. So the only place where, and you can see that the derivative, if z is 0, then you get 0, right? So, and we see one sees that f prime at 0 is actually 0. Okay, so this thing is it's not differentiable anywhere except at the origin. Okay. And at that point, it's bound to 0. Right? Even though, if we think of this thing as a real function, right? So, although that happens, although if we think of this as a real function, f of xy equals x squared plus y squared, this is has continuous partials of every order. And is thus differentiable as a real function. As a function from R2 to R2. So as a function from R2 to R2, this actually is a differentiable function. But it's not, but as a function, as a complex function, it's not differentiable, except at the origin. Okay. Has continuous partials of every order and is thus differentiable as a function from R2 to R2. Sorry.
How come you only check approaching 0 along the real axis in the imaginary axis?
Because that's enough to show doing those checking along those two lines only is enough to show me that that we're not going to be differentiable anywhere except for 0. Right? Like for the derivative to exist, this limit has to exist. Okay. Now if I if this limit exists, what is it? Let's see what it is. Well, if we let this difference tend to 0 along the real axis, we say that this thing is going to turn into this. If we do it along the imaginary axis, we say that it turns into this. Right? So the limit this had better be equal to this in order for the limit to exist. Right? But then that means that z is going to be negative z. Well, there's only one place where that happens. So by doing so, we establish that for any point other than the origin, the limit doesn't exist. Yeah, Mike.
You haven't shown that.
Yeah, that's what I was going to say. It's not sufficient to show that the limit does exist, that it's equal to 0, because
yeah, that's in this parentheses here. That's
they can approach them.
Right. That's in this parentheses here. So and one sees that f prime of 0 is equal to 0. Okay. How do you see it? Well, just look at this thing. Right. When z equals 0, what is this? It's going to be zeta bar. When zeta goes to 0, zeta bar goes to 0. So the limit is 0. So I sort of I mentioned it, I mean I didn't mention it explicitly enough. Okay. Is that okay? Do you all believe that it's we filled in the gap here? Okay. Okay. So and only a couple minutes left. So let me just make so I probably maybe I'll put it as an exercise. If f going from C to C is differentiable and f of z is real always, then f must be constant. And I don't know if this exercise exists in your homework, in your book, but if it doesn't, just add this one on. Okay? It's not. You can do. It's good. It's a fun thing to see. It's sort of cute, right? If your function, if you have a differentiable function and it's real valued, in fact, it has to be a constant function. Okay. And then just a remark about properties of. So one, if you take the derivative of a constant, you get 0. If you take the derivative of z to the n, then you get n z to the n minus 1. Right? Just like in calculus. And then a bunch of other things basically hold in exactly the same way that they do in the real plane. On the real line, differentiable implies continuous. The derivative of a linear combination of functions is, the linear combination of those derivatives of those functions, right? In other words, differentiability is linear. You have a product rule. You have a product rule. We have a quotient rule. We have a quotient rule. We have a chain rule. So there's a bunch of things that basically hold in exactly the same way that they did before. Okay, so we're not going to prove them. Okay, and the one last thing that I'm also not going to prove is that is the following proposition: if f is analytic. If E is open and connected, and if f prime is 0 everywhere, then f is constant on E. So it's basically the values at any 2 points are going to be the same values, and you do that by using a path, using the path by taking a path from one to the other and then differentiating. So I'll let you read it. It's not complicated.
Why'd you use 3 minus the equal sign?
Oh, is constantly equal to 0, so 0 everywhere, not just at one point, but it's always equal to. This triple line is constantly equal to. So now you know you have some idea of differentiability, and like I said, this will turn out to be an extremely constraining condition that will allow us to get all sorts of incredible results about differentiable functions. Okay, that's it for today. Thanks for coming.